Good afternoon, Math 153 students. We're going to start today with your first day of content, your first lesson. We are going to talk today with some fairly light content, maybe something that you've seen before in other classes. We're going to discuss the first statistic that we will talk about, and by statistic I mean way of describing characteristics of a set of data. We are going to look at the mean of a set of data, of a couple sets of data. In fact, I have a couple of sets written up here. Set A, 15, 12, 22, 16, and 10. And what we want as the mean is going to be sort of like a representative value that's in the middle. A mean is a type of measure of center. And we calculate that. It's a calculated average. That's what a mean is. And we do that by adding up all of the values that we have and then dividing by the number of values that we have so that the values are kind of spread evenly among all of the data points. So for set A, that's going to be equal to 15 plus 12 plus 22 plus 16 plus 10. All over, I have 5 data points, so we'll divide by 5. Adding all those up, I end up with 75. And if I divide that by 5, I get 15. Now in this class and in all of your math classes you should always stop, examine, and answer. Any answer that you arrive at, you should stop and you should ask yourself, is this reasonable? Does it make sense as far as what I'm actually aiming to get? We're aiming to get a measure of center, a representative value for this data set. And if we look at what we've got a 10 and a 12, kind of lower values. We've also got a 16 and a 22, a little up above. So they kind of average out at 15, and that seems reasonable. So just to summarize what we did sort of as a formula, and you have this on your in-class worksheet. To summarize what we did, I'm going to talk about the notation a little bit, what we're using. We're using the notation X bar. That is the mean of a sample set, as opposed to the mean of a population. That's going to be a different notation. But this is a sample set, so we're going to call it X bar, and we'll get to the difference between a population and a sample and how we calculate things a little bit later. But for right now, because it's the most commonly used thing, usually it's very, very seldom that we get to work with an entire population, and so we're mostly going to be using sample mean. So X bar is the mean of a sample, and that is equal to, this is a Greek letter sigma, and it is used to denote summing up a whole bunch of things. So sum of all of our x's all over n, where x would be an individual value in our data set. I'd like for you to take a second and practice this skill, calculating a sample mean with the second set, set B, 3, 6, 9, 9, 12, and 15. Have in your mind, though, before you even calculate it, have in your mind what you expect to be sort of the middle of a set like this, so that you know when you finish whether you've come up with something that makes sense or doesn't. Why don't you just pause your video right now for about 30 seconds or whatever it takes for you to go ahead and calculate this mean, and then resume and I'll have an answer for you. So pause right now, calculate that mean, and then come back to me. Okay, I calculated this mean and I got 9 for X bar. Hopefully you got the same thing. It does seem reasonable. That's a middle value. And it seems like a good representation of a measure of center for a set B. Now I want to start thinking about what happens if we manipulate this set. If we manipulate one of these sets, let's actually look at A. So what would happen if we, say, added another value in there if I added, say, another 15, what would happen? Because that was our mean for set A, right? What happens if I add in another 15? Do you have a guess? Well, if you guessed that this new set, would have a mean that is also 15, you're correct. And that is the case because, well, like we kind of described the mean to be, it's sort of like spreading out all of the value among all of the data points evenly. And if we've already spread out among these, all of the points in such a way that all of them, we can think of all of them basically like being 15. If I took some from this and stuck it on this and took some from this and stuck it on that, we could have like a whole set of 15s basically, and we would have the same total, right? That's what the mean sort of means. Well, if I just stick another 15 in there, then instead of having 5 15s that I'm dividing by 5, now I have 6 15s that I'm dividing by 6. So it ends up being the same amount, the same total after I divide, right? It ends up being the same mean after I add everything up because I'm adding another 15, but I'm also dividing by one more. So putting another value in there that is actually the mean doesn't change the mean of a set. However, if it's a larger value or a smaller value, it is going to change the mean. Say I added the value 20 into my set. Well, this is going to change the mean, and you probably guessed, it's going to bring it up, right? If I have a large value in there, then I've got some more points, basically, that I have to distribute, among the other data points if I want them to all be even, if I want to think of them as like all being even. So let's go ahead and calculate this. So we have 20 plus 15 plus 12 plus 22 plus 16 plus 10. All over this time, we're going to be dividing by 6, right? Because we have 6 values now. If we add in another data point, we have to make sure that we increase our n. So, okay, I crunched all those numbers, and I get 95 over 6 for my mean. If I want to think about that with some intuition, think about what that value would be. 90 is going to be 15 times 6. So we're going to have 15 and 5 6 more. So 15 and 5 6 is our new mean. And that makes sense. It went up. It almost went up a whole unit, right? If we had done, say, 21 instead of 20, then we would have had enough to give each one of the new values, each one of the 6 values, an extra 1, right? And we would have gone up to 16, but I didn't plan very well on that. So our new mean would have then been 15 and 5 6. Totally makes sense. Lifts it up, not quite enough to get it up to an increase of 1, but yeah, it lifted it up, and that's what we expect when we add a value that's higher than the mean. If we add a value that's going to be lower than the mean, it's going to drag it down. This mean is really susceptible to single value changes, as opposed to some other statistics that we're going to be talking about later that are resistant to large or small value changes. But mean is susceptible to that. It's very influenceable. So now let's look at a different way that we can alter a set of data to change its mean. Your in-class assignment asks you to take all the values in set A and multiply each of them by 5, so that our new set would be, let's just call it set C. 5 times each of these things. 15 times 5 is 75. Then we'd have 60. 22 times 5 is 110. 16 times 5 is 80. And 10 times 5 is 50. So we've got everything multiplied by 5. Everything's been multiplied by 5. And now we're going to calculate the new mean, our mean for set C. So keep in mind, there's a relationship here, right? Times 5. That's important. X bar for this set, by the way, we'll keep in mind that that is 15 for that original set. So if we multiply by 5, what do you suppose is going to happen? Well, I'll go ahead and walk you through it this time, but you're going to try it on your own with a different value here in a second. Let's go ahead and add up these values and divide by 5 to get our mean. Okay, I crunched all those numbers. There's no point in me sitting here adding up all these numbers in front of you. So I added all of our values on top, and we ended up with a total of 385 for our sum, our sigma x, and then 5 on the bottom. That's our n. Still have only n or 5 values for n. So if we divide 385 by 5, what do you get? Well, it's 75. What is the relationship between our original x bar for A, versus x bar for C? What is the relationship between 75 and 15? Take a second and think. Well, you might guess or notice that 75 is 5 times 15. If we multiply each one of our values individually by 5, then the mean of that set is going to be 5 times more. Let's do a little bit of algebra and see how that works. Maybe does it work in general, or was this just lucky because we happen to have 5 values and then we multiplied by 5? Was there some coincidence there, do you think? Or is this a rule that we can conclude? Well, actually what I'm going to have you do is do the same thing, only as your instructions say in the in-class assignment, do this with set B and multiply by 3. So we don't have that sort of like connecting value. The n is 6 here, we're multiplying by 3, so we can kind of rule out coincidence if you happen to see the same thing. See if you do. Give it a try, pause right here, and then come back to me once you have your answer. Okay, so if you calculated all of those products, multiplying each of your values in set B by 3, we should get this new set. I called it set D. We add up all of our individual values. There are 6 of them. I get a total of 162 and divide that by 6 and we get 27. How does that relate to 9? Well, it's 3 times it, right? So it seems like we can make a conclusion here. We have 2 examples that suggest a relationship. We can't claim that something is true based on just 2 examples, but it gives us enough information to be curious, to try to think about a way to see if it works in general. And in fact, this rule that we sort of suppose that if you multiply each of the values in a data set by the same number, the mean goes up by that factor as well, or down by that factor if we're scaling down. So we're going to actually prove that to ourselves algebraically. There is a rule that says that that's true, but again, we cannot claim that that's the case by just saying, well, it works for these 2 sets with these 2 numbers. We have to prove it. And it works pretty simply from the formula that we have for x bar to get there algebraically. So I'll show you that. First, I kind of want to reformulate our formula for x bar just a little bit. We're going to write it more explicitly. So we have the formula that you have on your in-class work that just says sigma x over n is our x bar. That just means, it literally means just adding up all of our n's, and there are n of them, or excuse me, all of our x's, and there are n of them. So I just expanded it and wrote it as an actual sum. And this little dot dot means whatever's in between 3 and n. That just means we add up all of those x's, counting them up to n, and then divide by n. So if we're going to multiply each one of the individual values by something, let's just say a, then we should get the new sum, ax1 plus ax2 plus ax3 plus axn. We didn't change the number of values though, right? We're still dividing by n. Well, if you know the distributive property, you know it works to sort of pass out a factor over a sum, but it also can be used sort of the other way to pull out a factor that's common to a whole bunch of terms and put it outside of some parentheses, sort of factored out. So this would be then equal to a times this sum without the a's well, look at that. This chunk of it is just that, right? So this is just equal to a times x bar. We can substitute that chunk that's exactly the same there and there. That's just x bar. We just substituted that value. So we proved it really, really simply algebraically. And it is true that if we multiplied each value in a data set by the same value, we're going to get that same multiple for the mean. Okay, continuing with manipulating means, we're going to see what happens now if we were to add or subtract something from each of the values. There are a lot of things in math that work for certain operations like multiplication or division, but they don't work for addition or subtraction. Let's see if the mean is one of those things, or if it also has some sort of characteristic of changing according to what we add or subtract on each of our individual values. So let's look at your in-class worksheet, and I think that it asks you to add 5 to each one of the values in set A. Adding 5 to each of the values in set A gives us this new set. We'll just call it, I don't know, set, well, I don't want to call it B, we'll just call it E, set E. Adding 5 to each of these, I'm going to get 20, 17, 27, 21, 15. Now to get the mean, remember x bar for A, still 15, x bar for E, we calculate this mean, 20 plus 17 plus 27 plus 21 plus 15, all over 5 still. That total on the top is 100, and we want to divide that by 5, so it looks like we have a mean for set E, x bar for set E is 20. Which is 5 more than the x bar for set A. So, wheels are turning, we're starting to think something's happening. Now I want you to go ahead and try the next problem on your own, see if you get the same result for adding a value to each of the data sets in set B. Add 3 to each of your data points in set B, and then find the sample mean right now, and then pause and come back to me when you're done. Hopefully you got what I got here. I calculated the mean after adding 3 to each one of the values in set B, and I found that the mean for the new set, I called it set F, I found that that mean is 12. So 3 more than the mean for set B. Do you think that this can be generalized? Well, again, 2 examples is not proof, but we can give an algebraic proof pretty simply from our formula for a mean, and we can see how this happens. So follow with me for this little algebraic proof. Okay, so once again, I used that sort of reformulation for our x bar. Instead of using the sigma, I actually wrote out the individual terms. If I add a to each value, then this is going to be my new x bar, the x bar for my new set, adding a to each individual value. But how many of those are there? How many a's do we have? We can use the commutative property of addition to group all of those a's together, and then there would be n of them, wouldn't there? There would be n a's because there are n different individual values, right? So n a's, and then we could rearrange so that the x1, x2, all the way to xn are together again. So x1 plus x2 plus xn plus a whole bunch of a's, n of them. N times a, all of this over n. And then using what we can think of as the distributive property of division, we're going to divide this group of terms by n, and then we'll divide that little piece by n. So if I have x1 plus x2 plus all the way to xn over n, well, what's that? That's our original x bar, right? But then we have n a over n. Well, those n's, if I divide n by n, I just get 1. So this ends up being, all of this stuff right here is just equal to x bar, our original x bar, and then this is n. So we've proven it. This works in general for any set, any sample set that is n terms long, that has n data points in it. This will work. To sum that up in words, what we just concluded is that if we add the exact same value to each of the data points in a set, that increases or decreases, if we're adding a negative number, the mean of the data set by the same value. I think the next question on your in-class assignment is a really good application for this. It makes us think of what happens if we add a certain amount to every single data set in or every single data point in a data set. Say we've got a group of 4th graders and then a group of high school seniors. Well, we know that they're not all going to grow in a uniform way, but we do know that if we take a set of 4th graders and then we watch them grow, we're going to be adding height to each one of them, right? From the time they get from 4th grade to their senior year, they're all going to grow a little bit at least, we hope. So increasing every single value in that data set is going to increase the mean of that data set, right? So if we take the mean of the heights of a set of 4th graders, we know that those individuals are going to be taller as seniors. And so in general, we can conclude that the mean for the seniors' heights would be higher than the mean for the height of the 4th graders. On your worksheet, just sort of summarize that in your own words, process it, and then write down what you think is the answer. This next couple of questions is pretty interesting. It's kind of conceptual. So we're trying to find a set of numbers, 5 numbers specifically, whose mean, x bar, is 290. Well, so what we're doing is we're asking, what is it that we could add together, 5 pieces that we could add together, such that their sum, when we divide it by 5, is 290. There's a pretty easy answer here. There's one that you might go to. Did anybody think of this one? It's a pretty simple one, right? If all of our values are 290, if I add them all up and then I divide by 5, I'm basically multiplying 290 by 5 and then dividing by 5, so of course I'm going to get 290. So that's a really simple answer. What if we wanted to do something different? Well, something that we could do is think about, well, 290 being smack in the middle and then having other values that sort of balance each other out. Because remember, this mean can be thought of as a way to distribute the points, or whatever it is that we're talking about, among the values evenly, right? So if 290 is the middle, but then if this number is a little bit more than 290, this is the same amount less. Say I had 300 and put this at 280. Well, right now that set of three values has a mean of 290 because I'm going to take one of the 10s, stick it on here, and then I've got a whole bunch of 290s. Well, I could do the same thing on these two outer values as well. I could take another 10 off. I could take 20 off if I want to. I could take down another 20 off of this and get 260. That would mean I have to just add another 20 to this, 320. So that those balance each other out. This one's 30 away from 290. This one's 30 away from 290 on the other side. So if I took 30 off of that one and stuck it on that one, I'd get 290 again. So we can think of this as distributing everything evenly in such a way that every one of them could be 290. So that's another way to do it. Come up with your own. It doesn't have to be as simple as mine. You can do something a little bit more creative, work a little harder at using these values to balance each other out. But go ahead and come up with your own. This next question allows us to explore this idea just a little bit further, that idea of sort of like passing out points among all of our values. We want to start with a set of, well, we're looking for a set of 6 numbers whose mean is going to be 290, but 5 of them are the same. So I'm just going to pick a random number. Maybe I'll just say 250 for my 5 that are going to be the same. Now, what is that last one going to be? I need enough points to distribute something from this number so that each one of my values goes up by, each one of these 5 anyway, goes up by 40, and this one ends up matching in the end. Take a minute and think about what might work there. There's only one answer here. Now that I've picked 250, there's only one answer that's going to work. Only one way to do this. So do this on your own and come back to me when you're done. Okay, did you come up with something? Well, I think that we need something that's going to have 5 40s to contribute to each one of these 5 250. So 5 40s, that's 200, right? And that value, once we got rid of all of those, if we think about the evening out thing, once we got rid of all those 40s, once we got rid of that 200, we would still have to have 290 left on this value to have our mean be 290. So it's like all of these are just a whole bunch of 290s, right? So it seems to me that the correct last value here would have to be 290 plus 200 more, so 490. Go ahead and take a minute and prove it to yourself that this actually works. I went ahead and calculated the mean this way. So I've got 5 250s, that's 1250 out of 490, and you get 1740. Divide that by 6, it's 290. Maybe you have a different sort of intuition, different way of thinking about a mean beyond this whole like passing out thing. Develop your own intuition here. Figure out your own way of thinking of what happens when we manipulate values in a data set, what happens when we scale up or scale down, add stuff. come up with some of your intuition and put it on the discussion board. We'd really like to, your classmates and I would really love to see what you have, what ideas you have, and ways you think about this. Okay, so this next problem on your in-class assignment is actually one that is super useful and probably one that you've actually done before in real life just because you needed to know, right? So you're given a situation where there are 4 exams in this class. 3 of them have been taken, and this person is really hoping to get an average of 80 on their test scores with one is a 72, one's a 58, and one's an 84. I'm thinking, hopefully you're thinking too, that he has to do really, really well on this last test, right? That 4 points above right here isn't a whole lot to distribute to these two lower values to bring them up to an 80. So we're going to actually use sort of the formula for a mean to calculate this. And we're just going to kind of rearrange it in an equation we're going to solve. And we're going to figure out what the unknown is. So we'll set it up. This is just basically the definition of x bar, the formula, adding up all the values. One being unknown, that doesn't matter. The formula still works the same. So T4 is left as a variable, the value for the grade on test 4. But x bar we're given. So this is good because that leaves us with only one unknown. We have a known value of 80 for x bar. Okay, so this will kind of reinforce this idea of sort of a balancing out. Whatever we have for T4, for test 4, has to make it so that when we divide this sum by 4, we get 80. Another way to think about that is thinking about the sum of all of the values as if they were just 4 80s. Right? If we'd gotten 80 on all of them, we would know that the average was 80. So think about it as 4 80s. This is how we solve an equation in one variable when we have division anyway. We're undoing this operation of division. So I'm going to multiply on both sides by 4. That cancels this division by 4 at the same time that I'm multiplying by 4 on the left side. So what's left here is just the sum. In other words, I need a total of 320 points for all of my tests so that it can basically be like 4 tests that had a score of 80 on them, right? So I need 320 points altogether. I have, if I add these up, I have 214 of them. So this T4 would be the remainder of what I have left, right? That has to be added to 214 to get 320. So I'm asking the question, what do I have to add to 214 to get 320? The way to figure that out is subtraction. So I just go T4 equals 320 minus 214. Again, just doing the inverse operations, we're just solving an equation here, right? So T4 has to be, this guy's in trouble. He has to get a 106. He has to get 106% on this test, this last test, to be able to get a score of 80. And we guessed this, right? We guessed that it needed to be a really high number. There was not a lot to work with to begin with. He got an F on the first one, or on the second one, just a C on the first one. He wasn't in good shape. So our suspicions were kind of confirmed. He needs something even more than 100% to be able to bring his grade up to an 80. And this last in-class question is just for you to connect your newfound understanding, maybe your hopes and dreams about this class, to what you see in the media. Statistics are used all the time to undergird a point that somebody is trying to make. They're trying to get you to believe something, and they can be manipulated. They can be sort of used in a way that is not mathematically sound to get you to believe something that isn't necessarily true. Maybe it will be technically true, but the way that it's said or the way that it's presented is misleading. So you got to understand all of those statistics and what they mean. We're not there yet, but go ahead and find yourself an example. They're all over in the media. They're used to prove points or give evidence anyway, very frequently. So come up with your own example, somewhere where you've seen a statistic used in the news.